Okay, this is a recording of the 1.5b notes. So in this particular group of notes from 1.5b, we're going to work on graphing logarithmic functions to start with. The directions on this say, draw the graph and determine the domain and range of the function. Rewrite the logarithm in exponential form and plot at least 3 quality points. Identify any asymptotes that may occur. Let's start with the domain. As always, we do have another domain restriction that we need to consider. When we are talking about logarithmic functions, and I changed this to a circle, so hopefully it's a little bit easier to see the cursor now. Okay? When we're talking about logarithmic functions, we cannot take the log or natural log, so any logarithm, of a negative number or 0. Remember, when we're finding a logarithm, we're actually trying to find the exponent. What is the exponent? Y given a base of 2 that would produce an x plus 1 is essentially how we're looking at this. Well, negative situations create problems. So we know that this argument has to be greater than 0. So the very first thing I'm going to start with is the domain. I'm setting x plus 1 greater than 0. I don't need to write that down. I can subtract 1 from both sides and realize that the domain is the set where x is the element of all real numbers such that x is greater than negative 1. It will not equal negative 1 because we cannot take the logarithm of 0 either. So parentheses, negative 1 comma infinity is how it's written in interval notation. The range is written here. It is all real numbers, as you can somewhat see from the graph. And that is typical for most logarithms, but occasionally we can get some range restrictions. So the range here is all real numbers, and again, written in set builder and interval notation. But being able to graph logarithmic functions, I don't want you to just recognize that this is a log base 2 shifted 1 unit to the left. That's essentially what it is. It's a transformation here. However, I want detailed points because you can give a nice detailed graph by rewriting this as an exponential equation. So what do we mean by writing this as an exponential in exponential form? Well, the opposite of log base 2, the inverse operation to that we learned, is 2 raised to the y. So if I take 2 raised to the y on both sides, I take both sides and I take 2 raised to that. On the left side, I'll get 2 raised to the y. And over here, the 2, the base of 2, will cancel with this log base 2 because they are inverse operations, and we'll just be left with the argument. Some people choose to think of this as base is 2 raised to the exponent because logarithm equals exponent. Base raised to the exponent equals the argument. That's how I will say it a lot of times. Base raised to the exponent, the logarithm equals the exponent. Set that equal to the argument. And then I can subtract the 1 to the other side. And now I have this nice exponential form. The only difference is I'm going to plug values in for y and figure out what x is. Just like I do for a lot of relations. This actually does turn out to be a function, but we're going to plug in values for y and figure out what x is. Let's start over here. I probably should start with this value, the most interesting value of y. Remember, I'm plugging in y. I say up here input so you can see it. If I plug in 0 for y, 2 to the 0 is 1, 1 minus 1 is 0 back out. That's a quality point. If y is 1, 2 to the first power is 2, minus 1 is 1. If y is 2, 2 squared is 4, and 4 minus 1 is 3. If I plug 3 in, 4y, 2 cubed is 8, 8 minus 1 is 7. I even plugged one more in just for good measure. 2 to the 4th power is 16. 16 minus 1 is 15. But what happens then if y becomes negative? So what if I go the other direction from 0, from this most interesting value of y? If I plug in negative 1, I'm going to talk through this. 2 to the negative first power is 1 over 2 to the first power. That's 1/2. 1/2 minus 1 is negative 1/2. Plug in negative 2. 2 to the negative second is 1 over 2 squared. 2 squared is 4, so it's 1/4 minus 1 is negative 3/4 for x. Plug in negative 3 for y. 2 to the negative third is 1 over 2 cubed, or 1/8. 1/8 minus 1 is negative 7/8. It shouldn't take long to realize this negative 4 is going to produce a negative 15/16, and I could keep going. The larger the negative value is that I plug in for y, the closer this x value is getting to negative 1. That's why x equals negative 1 is the vertical asymptote. If exponential functions had horizontal asymptotes, then it would make sense that their inverse function, which is logarithmic function, has vertical asymptote. X equals negative 1 is the vertical asymptote because that value of x makes the argument equal 0. And we can't take the logarithm of 0, so it's undefined. If I plot these points and connect them together, I get this look right here. Now be careful, if you try to graph this in your graphing calculator, a lot of times the graphing calculator will come and it looks like it stops right about here because it gets so close to that vertical asymptote it cannot graph another point. But the graph really doesn't stop. It gets closer and closer and closer to that vertical asymptote. Okay? So we covered the rewriting, domain and range, vertical asymptote, point plotting. Remember, we're plugging values in for y to figure out what x is. We just need the intercepts. To find an y-intercept, we simply plug in 0 for x. What is log base 2 of 1? It doesn't matter what the base is. If I want to get 1 out, the exponent has to be 0. But better yet, this is actually easier to find the x-intercept by plugging 0 in for y. And we stumbled upon it right here. If the origin is an x-intercept, then it also is the y-intercept, right? So the origin in this case is both the x and the y-intercept. Okay? That's a nice, easy one. This would be more like what I would put on a test or quiz just to make sure that you understand the inverse nature between exponential functions and logarithmic functions. But here's a second example. And we are going to deal with more natural logs, but I probably would not put a graphing of a natural log on the test. I want you to be able to get good quality points and show that you can point plot this. The base, remember ln is just short for log base e. Instead of having to write 4 letters every time, we just cut that down to ln for natural log. Let's start with the domain. If I set 3 minus x greater than 0, it cannot equal 0, and add the x to the other side, 3 is greater than x. Well, 3 is greater than x is the same thing as saying x is less than 3. Here's the domain in set builder notation. Here's the domain in interval notation. Okay? The range, again, if you want to write it down quickly, is all real numbers. This graph is going to go down forever and go up forever. And that is typical of logarithmic graphs, but not always. So after determining the domain, why not stick with the same type idea and determine the vertical asymptote right away and dot that in, because that's going to help your graph evolve. The vertical asymptote always occurs for whatever value of x makes this argument equal 0. 3 minus x equals 0 when x equals 3. So there is the vertical asymptote. We dot in this vertical asymptote. We got the domain, we got the range, here's the vertical asymptote. Now let's see if we can graph some points and show how it's approaching this vertical asymptote. Is it coming this way like we have graphed here? Maybe it's going this way. Okay, and you could go through your transformations, but I want you to be able to rewrite this in exponential form, because these logarithmic properties are going to be very important when we solve equations later on in calculus. First of all, I cannot undo this natural log until I have a natural log and an argument only on this side. And that's going to be true throughout the year. So if we have these other values, like a coefficient in front of the natural log and this number subtracted from it, we have to get these numbers to the other side first. So the first thing I'm going to do is add 4 to both sides of the equation. But we have to divide by 2 before we can undo the natural log. And sometimes students forget to do this. The easiest way that I can explain it is before we can eliminate the natural log, we must have a natural log and an argument only on one side of the equation. Now, what is the inverse operation of a natural log? E raised to. So I took e raised to both sides. E raised to this side equals e raised to this side. Well, e raised to a natural log, the e and the natural log are inverse operations. So I'm left with the argument of 3 minus x. If I add x to the left side and subtract this entire term to the right side, I now have an exponential form for this function. The only difference is I'm solving for x in terms of y, because y is going to be my input when I try to plot some points. The most interesting value of y here is negative 4. Negative 4 plus 4 is 0. 0 divided by 2 is 0. E to the 0 is 1. And 3 minus 1 gives an x value of 2. That's why I have the point 2, negative 4. That's the only really solid point we're going to get. Because e, remember, is a non-repeating, non-ending decimal. The value of e is 2.71. We'll actually take a limit to show how this value evolves in the next chapter. For now, you need to know it's 2.71. Should have done that in pre-calculus a little bit. So if I'm going to pick other values for y, I certainly do not want to pick odd values for y. I want to have a value that's going to divide by 2 nicely. So I picked y equals negative 2, because negative 2 plus 4 is positive 2, and 2 divided by 2 is 1. It's e to the first power. Now, I did not write the decimal approximation because we should be able to somewhat tell what this is. This is 3 minus 2.71, right? So it's about 0.29. We can do that without a calculator if you know the value of e. It's about 0.29. So if I go to the right, about 0.29, I'm going down negative 2. If I go to the right 2, I'm going down negative 4. Really, those 2 points are going to tell you how you're approaching this asymptote. But let's just look at a couple more. Okay? If I plugged in negative 6 for y plus 4 is negative 2. Negative 2 divided by 2 is negative 1. E to the negative first power is 1 over e. It's some number between 1/2 and 1/3. So 3 minus that is going to be somewhere between 2 and 2.5 and 2 and, if it's a third, 2 and 2/3, right? So a little bit more than 2.5. That's what that value is. So if I go to the right about 2.5, I'm going down to negative 6. Let's go the other way just to see what happens if we did pick a 0 here, okay, from this most interesting value. If we pick 0, we get 4 divided by 2 is 2. E squared is going to be larger than 3, so you get 3 minus this negative value. Okay, it's going to be back here. And we can sketch those together. Now, you can use your calculator. I don't want you to think that you can't use your calculator. Use your calculator on these values. I'm just trying to show you that if you know the value of 2.71, you can get reasonable approximations as you graph it. Okay? And again, I'm not going to put a natural log graph on the actual test or quizzes. How do we find the x and the y-intercept? To find a y-intercept, plug in 0 for x. Well, if we plug in 0 for x, we get 2 natural log of 3 minus 4. There's not much we can do with that. Just write it. 2 natural log of 3 minus 4. You can find the decimal value in your calculator, okay, and see if that is about the value that you're going through. To find an x-intercept, plug in 0 for y. Well, we did it right here. We already plugged in 0 for y. We got that. So that's the analytical answer. I did convert it to a decimal so I could graph it. Back 1, 2, 3, 4, and a little bit more. There is the x-intercept. So I used that x-intercept to give me a nice detailed graph. Again, not likely to put a graph of a natural log on tests or quizzes. I want to see if you can plug in good values for y and get out good values for x and get a nice detailed graph. So in all likelihood, the base will be 2 or 3. So you get out decent numbers. Okay, solving some equations algebraically. We've already done this in section 1.3. That's why I did it right away. So this shouldn't be a new concept, at least not for A. If I want to solve this equation, the key is if I'm solving for a variable that's in the exponent, my first choice is to try to get the bases to be the same. I cannot rewrite 1.045 as a base of 2. So I have no choice but to take the natural log of both sides. Why do I want to take the natural log of both sides? Because I have a logarithmic property that allows me to drop this variable down in front of the natural log. That property says if you have a base raised to an exponent in the argument of the logarithm, the exponent can drop down in front of the logarithm. Now this is just a number. Divide both sides by the natural log of 1.045. And here it is. And they're trying to give you values. I think you actually run into this in some of the word problems. If you type that into your calculator, you get 15.747. And notice that we're using T here, so that's probably years or days in some type of practical application. Okay? Example number 2, B, is the toughest one. Okay? I'm going to show you this process algebraically, remembering that we can always solve this equation using our graphing calculator by graphing the left-hand side as y1 and the right-hand side as y2, and then finding where those two functions intersect. That will give you the decimal answer. But I want to show you this technique. It's an algebraic technique that we're going to use frequently in calculus. If I'm trying to solve this algebraically, I might try to make this exponent positive. For lack of anything better to do, I might rewrite this portion of this equation as 1 over e to the x. And then when I look at this, I would say to myself, you know what's making this problem confusing is this e to the x business. If I just didn't have this e to the x in there, maybe it wouldn't be so hard to solve this equation. So we do this a lot in algebra and in trigonometry, where we say, let's try to make this a little bit easier, okay, if I replace e to the x with a u. Now, I multiplied everything by e to the x here first. I probably shouldn't have even have done that. I should have just replaced with u right away. Okay? But if I multiply this by e to the x, I get e to the x squared. If I multiply the fraction by e to the x, I cancel. Here I get 3 e to the x. But this e to the x, that's what's creating the problem. So I'm going to try to clean this up by saying I'm just going to make e to the x equal u. And u is a very common variable that we use for this process. It's called a u substitution. Okay? But there's nothing special about u. You can use whatever variable you want. You're just going to see u a lot throughout the year. So I replace e to the x with a u. This is u squared. Subtract this term to the other side. I replace this e to the x with a u, minus 3u. There's a plus 1. This is a nice quadratic equation. I can solve quadratic equations. Hopefully it's factorable. Nope. Not very nice. That the first quadratic we see is not factorable. So we have this thing called the quadratic formula. We need to know the quadratic formula for sure. It will pop up throughout the year. I don't put it on tests and quizzes because I have not seen it on the AP test. I don't know if ever. factoring is going to be more important. But here it is. Negative b plus or minus the square root of b squared minus 4ac all over 2 times a. We get 3 plus or minus the square root of 5 over 2. So you should have done it enough. And if it does pop up on the AP test this year, we'll see it throughout the year. Okay? But that means that I have 2 values for u. I need to solve for x. Well, I just plug those values for u right back in here. And I write this equation right here. If I want to solve for x, that variable is in the exponent of e. How do I undo e raised to? That's why we have the natural log function. It is the inverse function of e raised to. So we essentially take the natural log of both sides. Take the natural log of this side, it's right here. The natural log of e to the x just gives me an x. So I just wrote x equals the natural log. I'm just taking the natural log of both sides so I can solve for x. When I type this into my calculator, be careful. The natural log, parenthesize the numerator, divided by 2, then close it. You should get these 2 values. I'm going to quickly show you on the calculator here how to do this, and then I want to show you we can check this answer graphically as well. So let's go to the calculator here and take a look at this. First of all, let's just type in these answers right here. 3 plus the square root of 5 over 2, the natural log of that. When we type this in, I'm going to go natural log. It already gives me a parentheses, but I'm going to go parentheses 3 plus second square root of 5. I'm going to cursor to the right. I'm going to close that, so I'm done with the top. Divided by 2, close the parentheses, and hit enter. There's one of the numerical solutions. So I don't have to type this all in again. If we just go second enter, it will type up the last entry that I have. And I can come back here and just change this plus sign to a minus. That's all I want to do. And I get this. The exact same value, but the negative. Interesting. Let's see if we can solve this graphically as well. Remember, the original equation here was e to the x plus e to the negative x equals 3. So I'm going to go to y equals. I'm going to graph the left-hand side. Second natural log will give me e raised to. I'm going to put an x in, cursor to the right, plus second e raised to. I'm going to put a negative x in here. I'm going to cursor to the right. Let's just graph this piece so we can take a look at it. I'm going to go zoom 6. It's working at it. There it is. Well, that's an interesting graph. And I want to know, when does this graph equal 3? So I just graph the right-hand side as 3. Oh, this makes sense now, that I have an x value that's negative and an x value that's positive, because it looks like this graph is an even function, and it is. How do I find these solutions? Second calc. 5 for intersect. Cursor to the right, get as close as you can to the intersect, and hit enter 1, 2, 3 times. There's the answer that we had. Just in case you want to see it one more time, second trace for calc. You'll be in the calculate. I want to calculate an intersection point. 5 for intersect. I'm going to cursor to the left until I get close to the point of intersection, and I hit enter 1, 2, 3 times. Okay, sometimes got to work at it. Oh, that's not good. Let's try it again. Second calc. It looks like it's frozen here. Okay. It will give you the same answer here. I'm not quite sure why this froze up on me. Okay. So that second one, the calculator froze up, but it will give you the same value when you check in your calculator. Okay? So finish up this. Probably this problem here, this one here is nice because of this technique. Not going to be on a test or quiz. We will use that technique later on in calculus. But this is going to be very important. There's quite a few steps here that are critical. First of all, if I want to solve for y, there are 1, 2, 3, 4 terms in this equation. Only one of those terms involves a y. I need to get all terms that do not involve a y away from this term. So I have to add the natural log of 3 to both sides of this equation. It will eliminate the natural log of 3 on this side, put a plus the natural log of 3 on this side. I have to have a natural log and an argument only when I'm trying to solve for a variable that's inside the argument of that natural log. I cannot take the natural log of both sides until I've isolated this scenario. But now I can undo this natural log function. The inverse of natural log is e raised to, just like the inverse of x squared is the square root of x. So I take e raised to this side and e raised to this side. Notice I took a step here just to rearrange a little bit, and then I used a property for logarithms to rewrite this. The natural log of 3 minus the natural log of x, I can combine those. If I'm subtracting natural logs, I can make it one natural log and divide the arguments. So I rearranged and I applied some logarithmic properties. But now I want to undo this. So I take e raised to both sides. If I take e raised to this side, I get a y plus 1. If I take e raised to this side, I get this look right here. Here is, I can solve for y by subtracting 1 to this side. But they will never leave a natural log in the exponent of e, because these are inverse. They're inverse properties. This e can undo this natural log. I just have to rewrite it first. This step from here to here is the step that tends to give students the most difficulty. I put an asterisk by it. You may want to highlight this. When I'm going from this step to this step, I'm simply using the Algebra 1 property that says this. When I multiply like bases, I can add the exponents. I'm just using that property in reverse right here. If I'm adding exponents, I can write it as a multiplication of like bases. We're going to use this step a lot when we're dealing with e raised to situations. If I have a natural log in the exponent of e, I'm always going to use this property that says when I add exponents, I can treat it as a multiplication of like bases. Just like if I multiply in like bases, I can add the exponents. It's just the reverse of what you typically have used it in the past. Why would we want to do that? Because now this e is raised to this natural log. They undo each other. And we're just left with 3 over x. There it is. So it's 3 times e to the x over x. Now I subtract the 1 to the other side. This is a much cleaner form than this. Here's when you really need that you need to know that you have to clean it up. If you have a natural log in the exponent of e, that needs to be cleaned up. If it is part of an addition or subtraction in the exponent, then you have to use this algebraic property to make it a factor first. The most common mistake is that students will skip this step and they'll put plus 3 over x here. That's not true, right? I cannot let this e undo this natural log until it's written as one factor here. That's why I have to utilize this property. This step right here, there's an asterisk, but we have to know how to use this algebraic property in reverse. We probably use it just as much this way in calculus as we do going this way. Okay? So keep that in mind. Okay? Probably just as much this way as we do going that way. Okay? So there it is. You're going to have a problem like that on the worksheet, and I explained that as well. Okay, so make sure you work hard on the worksheet, and I'll make a video of that here next. Okay.